Shri Gurubhyo Namaha, children. Today we are going to the second topic, which is a very interesting and also important topic, current electricity. Now, last chapter, that is in electrostatics, we were learning about static charges. Static charges in the sense the charges that are at rest. Static means not in motion. So we were talking about, or we were learning about the properties of static charges. Okay. Now this chapter we are going to talk about charges that are in motion. Now whenever we define the definition for current, we state that current is nothing but motion of charges, right? So suppose if you take a conductor or a material, now these charges are always moving in the material, right? Suppose for example, let us take a wire, okay? Now in this wire, electrons are randomly moving and you cannot say that the electrons are at rest. So definitely you have to analyze the behavior of charges when it is at motion. Okay, the motion of charges is called electric current. So whenever we study the motion of charges, it constitutes what is called as an electric current. Okay, right. Now there are so many examples. Without current you can say that there is nothing possible now. Okay, wherever you go you need current. Communication or operation of electronic gadgets nowadays, our online classes, you cannot imagine without current. If the data, battery, charging, laptop, all these things require current. So communication system, electronic devices, home appliances, so everywhere you need current. So definitely it is for us to learn about what is called as an electric current. And apart from that, in this topic we are going to talk about, first of all, flow of charges. Then we are going to talk about, we are going to learn about Ohm's law, resistance, resistivity, conductivity, then about carbon resistors, temperature coefficient of resistance, then Kirchhoff's law. Kirchhoff's law, you have current law, voltage law, then Wheatstone's network, potentiometer, meter bridge, so many concepts we are going to talk about. And finally, heating effect, Joule's law of heating. Okay, so all these topics we are going to cover in this lesson, right? So let us move on uh, to know about what is called as an electric current. Okay, so whenever we talk about matter, okay, matter, how matter is made up of? Matter is made up of atoms, and you know that in each atom you have a positively charged nucleus and you have negatively charged electrons. Now these electrons near the nucleus, they are bound to the nucleus, but outer, that means which is at a far distance, electrons that are at a small separation of distance from the nuclei, that is the outermost electron, they are free to move. Okay, so whenever we talk about atoms, now atoms in metals which are termed to be conductors, they have more than one electron which are loosely bound to the nucleus. So these electrons can move freely. And since these electrons can move freely, they are called as free electrons. So what are they called as? They are called as free electrons. Okay, and these free electrons, when you have more number of free electrons in a material, you call that material as a conductor. Okay, in a conductor, the movement of free electrons takes place and the movement of charges is nothing but you call as current. Okay ma, right? But in a conductor, these free electrons are moving randomly in the sense here and there. Okay, not in a steady direction or something like that. No, these electrons in a conductor which are excess, you call those electrons are free electrons, and these free electrons move randomly throughout the conductor. Okay, so due to this random motion, now what will not happen, in the sense transfer of charges. Now there is no transfer of charges from one end of the conductor to the other end, and you cannot say that current is flowing. There is no current in the wire. So this is as such when the conductor, suppose for example, this is the conductor. Again, this is a copper wire, no doubt about that. There are two ends, and here these ends A and B are said to be at the same potential. So when there is same potential, that is when we talk about electrons moving randomly here and there in a conductor, you have the potential to be same. So you cannot say, you can say that there is no current in the wire. Okay, so whenever there is no potential, whenever there is not an external energy, if there is not going to be any external energy, the electrons as such, they move randomly here and there, and while they move, they hit the positive ions. Whenever we talk about a material, suppose if this is going to be a material, now this material is made up of protons, electrons, neutrons, everything, and protons are considered to be the positive nuclei. Okay, it is consists to be of positive charges, which is considered to be highly massive than the electrons. So these protons are not able to move. So which alone will move? Electrons will move, and when they move, they will come and hit this positive charges. Okay, we have what is called as collisions. So, and these collisions occur randomly here and there, and there is no current that is produced. Now this is in the absence of any external energy. Okay, all the electrons, they are free to move, they move randomly. Now what am I going to do is, I'm going to connect this to an external battery. Now look at this wire. Now this is wire. Now this wire is connected to an external battery which has got two terminals. Now this is the negative terminal of the battery and positive terminal of the battery. Now hope you have seen these type of batteries in the shop. Okay, so there are two terminals, and this plus terminal is said to possess positive charges, which is considered to be at a very high potential. So this plus is at a higher potential, right? And this minus is said to be at lower potential. Okay, so you connect this wire to the two terminals of a battery, which is at a higher potential and a lower potential. Now what happens? Now what happens to the electrons here? Now the electrons that are free electrons present in the conductor, as soon as you give an electric field, they start moving towards the positive terminal of the battery, because electrons are considered to be negatively charged. These free electrons, they start drifting. Look at the word drifting. It's a very important word, drifting towards the positive terminal of the battery. They start moving. Before the presence of electric field, all the electrons were moving randomly. But after you give an electric field, or after you are connected to an external source, all the electrons which are moving here and there, now they start moving, or they start drifting towards the positive terminal of the battery. So when electrons start moving, what happens now? There will be a current produced in the battery. Are you able to understand? And whenever you have charges moving from a higher potential to lower potential, now here positive charges are there. Now this plus is considered to be at a higher potential, and negative is considered to be lower potential. So positive charges, they move from higher potential to the lower potential, and negative charges will move from lower potential to higher potential. Okay, so what is the work of a battery here? The battery produces a potential difference. Now this is at a higher potential, this is at a lower potential, so definitely there will be what is called as potential difference. Okay, so a battery or a cell, it can create a potential difference across a conductor. Now the charges start moving and current is produced in the circuit. Is it clear, children? Now let us go on to the definition of what is called as an electric current. Right. Now look at this diagram. Now this is a conductor. Okay, and charges are flowing inside the conductor. Hope you can understand the diagram. A small area. Now charges are moving here. The charges at the left side, they are entering, and here they have already passed through the conductor. So what is the amount of charge? I will write here, children. When you define electric current is nothing but rate of flow of charges. Now rate in the sense with respect to time. Now what is the time for the charge to cross an area? Rate of flow of charges through a given area is nothing but you call it as electric current. Okay. Now I'm going to give a formula for electric current. Now let us consider that there is a net charge. There is a net charge Q flowing through any cross-section area of a conductor in time t. Now this, why we take time t here is, now time plays a major role because we need to know, suppose this area is a bit larger area, suppose there are smaller areas also. So if the area is going to be smaller, the amount of charges entering will be less. Now here you have more amount of charges to be entering. So definitely how much amount of charges are flowing through in a conductor with respect to a particular time has to be taken into account, because the time will not be the same everywhere, it will be varying. So definitely time should be taken. Okay, so if a net charge is passing through this conductor at a particular time, then the current is defined as I is actually this is the definition for current, Q by T. Very important formula. I is equal to Q by T. Okay, and you cannot say that the charge flowing in a conductor is always constant. It need not be constant, it may change. That's what, if the area is not going to be the same, then current need not be same. So in that case, how the formula will change, then you will take average value of current at a particular point, current at a particular point, current at this point, that point. So all the values together, you have what is called as average value of current. I average is equal to del Q by del T. Now this can also be written as dq by dt. Now here the formula rearranges at a particular point. If you want to find out current at a particular point, you call it as instantaneous current, because as I said you, the current need not be same, it may vary. Okay, so in that case I can write the value. Now this is also correct, and I have one more formula for current, which is I is equal to limit del t tend to 0. You have del q by del t. Del q del t, it's a small value of current which is also given as dq by dt. Now this is also the formula for current. Here you call this as instantaneous current. Hope you are very familiar with this word, instantaneous current at a particular point, or which is given produced instantly. You call that current as instantaneous current. So in that case, the formula goes like this. So these two are also very important formulas related to current. Now we are going to talk about instantaneous current and average current. Now instantaneous current is current with respect to a point. Average current is you take the current of all various points and club together, you call it as average point. That is, in average current, we have the values to be 2. dq will be, you are going to consider two charges here, q1, q2. and dq will be q2 minus q1. Similarly, dt will be t2 minus t1. But here it is not like that. We have a particular charge, you have a particular time. So in that case, you call it as instantaneous current. Hope you understand the difference between these two. When the time interval is given, when the charges are given, then here you will go for average. Here, when at a particular point, whenever we talk about the charge is this and find out the current at t is equal to 5 seconds, in that case it becomes instantaneous current. So these are some of the formulas about current. On the whole, we can define current to be the rate of flow of charges. I is equal to q by t. Okay. Now let us go to the unit of current. What is the unit of current? As I told you, the formula for current is I is equal to q by t. Now the unit of q is coulomb and the unit of time is second. So coulomb per second is the unit of current, or ampere. Ampere is a very, very important word. Okay, the unit of current is ampere. Right? Now, let us take 1 coulomb of charge. Okay, 1 coulomb of charge passing through a perpendicular cross section in 1 second. Then the current is said to be 1 ampere. Suppose let us take the Q value to be 1 coulomb and S value to be 1 second. 1 second. Then the current is said to be 1 ampere. 1 ampere equal to 1 coulomb per by 1 second. This is also the formula for current. So when the current is said to be 1 ampere, when 1 coulomb of charge is passed over any cross section area in 1 second, then the current is said to be 1 ampere. Okay, ma? And whenever we talk about current, current is a scalar quantity or a vector quantity. Current is a scalar quantity. It is a scalar which has got only magnitude. Okay, there are some situations where we are going to consider current, but not now. As such, whenever we talk about current, current is a scalar quantity. Right? So these are some of the things which you should know about the introduction of current. Okay, now let us move on to the conventional direction of current. This is also very, very important, children. What is the direction of current or conventional direction of current? Okay, now look at this diagram. Now here arrow heads are given and you connect a bulb or a filament. Here it is an electric bulb. You connect this to a battery. Now this is the positive terminal of the battery. This is the negative terminal of battery. Now whenever we draw arrows, the arrow heads. Now this is the head of the arrow. Okay, now this represents and whenever you have I symbol, this is the direction of current. Okay, green color arrow represents the direction of current. And what about this red color arrow? Now this represents the flow of current, flow of electrons. Okay, now listen. Now arrows are used, arrowheads are used to indicate the direction of current. Now conventionally, the current flow is considered to be from positive terminal of the battery to the negative terminal. So if this is going to be the positive terminal, current conventional direction of current is from positive terminal of the battery to the negative terminal of the battery. Okay, now this is nothing but you call it as conventional current. But whenever we talk about current, current is nothing but it is the movement of charges. Now which is moving here? It is nothing but electrons. They are considered to be the free charges that move inside a conductor. So what is the flow of electrons? The electrons will move from the negative terminal of the battery to the positive terminal. Okay, so the conventional direction of current is from positive to negative, which is opposite to the flow of electrons, which is from negative to positive. Hope you understand. So the flow of electrons and the direction of conventional current, they take place in opposite direction. Is it clear, children? Once again I repeat, the direction of conventional current is considered to be from positive to negative terminal, which is opposite to the flow of electrons, which is considered to be from negative to positive. Now this is what they have mentioned here. Now this green arrow talks about the conventional direction of current. Here the red arrow talks about the flow of electrons. It depicts the flow of electrons here. Now this is the direction of current. Okay, so when you say mathematically, the transfer of positive charge is the same as that of a transfer of negative charge, but they take place in the opposite direction. Is it clear now? Yes or no? So conventional current, I'll write here, conventional current is from positive to negative terminal, whereas flow of electrons is from negative to positive terminal. So this is about conventional direction of current. Okay, now with this we are moving on to a very important topic, which is called as drift velocity. Okay, as I told you in the introduction, whenever we talk about a conductor, in a conductor, what are the charge carriers? The charge carriers are considered to be nothing but electrons. Okay, now these electrons move very freely through the conductor and they colloid with the positive ions. As I said, there are positive charges that are also present in a conductor. Okay, imagine this to be a very small conductor. Now positive charges excuse me, children, positive charges are there. Now among these positive charges excuse me, you have electrons. So these electrons are considered to be freely moving in a conductor, and these positive ions are fixed, they cannot move, and whenever these electrons are moving randomly, they come and hit these positive ions. Okay, so they colloid with positive ions, they colloid repeatedly with the positive ions, right? Now in the absence of electric field, or if there is no electric field, these electrons will move randomly in various directions. Okay, and whenever the electrons move, they possess some velocity. Yes or no? Whenever moving charges, they also possess some velocity. Now what happens to the velocity here? The velocity tend to be also moving, and the net thing will be 0. Yes or no? They move thermally. Thermally means increase in temp. There will be a temperature which is producing some heat. So they collide thermally with the positive ions, and they possess some velocity which is considered to be 0. When you take the average velocity of all the electrons, it tends to be 0. That is why in the absence of electric field, that is why we say the charges are neutralized in a conductor in the absence of an electric field. Yes or no? Right. Now, so there is no net flow of electrons, because one electron, now as far as the moment of concern, this electron will be moving in this direction, another electron will be moving in this direction, another electron will be moving in this direction, another electron will be moving. So the net flow of electrons as such is considered to be 0, and as far as this conductor is concerned, there is no net current. But when I connect this conductor to a battery now, okay, now this is again a conductor, positive charges are there, and in between you have what is called as electrons that are moving very freely. Now I am going to connect this to an external power supply. I am going to connect it to a battery. Now this is the positive terminal of the battery, This is the negative terminal of the battery. So when I connect it, now immediately what is created here? A potential difference is created. Yes or no? There is a potential difference that is created by a conductor, and definitely there will be an electric field which moves in this direction. Electric field will move from positive to negative. Yes or no? So there is an electric field created in the conductor. Now this electric field, what happens when these electrons are acting in this electric field? Definitely they will experience a force. Yes or no? So what is the force experienced by the electron? We know the formula for electric field. Electric field is equal to force per unit charge, or force is equal to E into Q. Now as far as our topic is concerned, the charge is nothing but the charge of an electron. So whenever an electron is kept in an external electric field, definitely it will experience a force. Yes or no? Now this force makes the electron to drift to one direction. So whenever an electric field is given, the electron starts drifting towards the positive terminal of the battery. They get accelerated. Already they have what is called as thermal velocity, right? In the absence of electric field, they possess thermal velocity due to the collision by the positive collision with the positive ions, and we found out that the net thermal velocity is zero because there is no electric field. Whereas in this case, when the electric field is given, the electrons gets accelerated. They get more energy, so they get accelerated, and once again they go and hit the positive ions, and they try to have a zigzag motion that is given in this diagram, children. They have a zigzag motion, and they start moving towards the conductor in a direction opposite to that of E. Now this is the electric field direction, positive to negative. Now what should be the movement of electrons inside here? It should be from negative to positive. So this is how the electrons drift towards the positive terminal. They get accelerated when an electric field is given. So they possess velocity which is called as drift velocity, Vd. Vd is nothing but, you call it as drift velocity. They start drifting towards the positive terminal. Okay, and this drift velocity is nothing but, it is the average velocity acquired by the electrons. Average velocity acquired by the electrons is nothing but, you call it as drift velocity inside the conductor. Okay, now after they gain velocity also, they will not stop moving, hitting the collision, hitting the positive ions. So suppose let us consider this to be a positive ion. Now the electron, I told you this positive ion is fixed, they cannot move. So what happens to this electron? This is an electron. Now this electron will come and hit the positive ion, go. Okay, again it will go somewhere, again it will come and hit the positive ion and go. So they keep on colliding with the positive ions. So the time interval, now suppose let us take the electron is coming and hitting this positive ion, then again it is going somewhere, then once again it comes back, it comes and hits this positive ion. So the time interval between two successive collisions means this is one collision, again it goes, come back, hits again. So successive collisions, what is the time interval between those two successive collisions? You call it as relaxation time. Now that is represented by tau. Okay, so the average time between two successive collision is called mean free time. You tell it as mean free time, which is represented as tau. Okay, and we know the formula for F is equal to m into A, or A is equal to F by m, and these electrons will experience a force E into E by m, and we have the formula for velocity as Vd as A into tau. A is E into E by m into tau. Now this is the formula for drift velocity. Okay, and this E into E by m is also called as mu which is called as mobility. So Vd is equal to, I can write mu of, sorry, here it is E into tau, it should be. Okay. So mu is equal to, Vd is equal to, so I have E tau to be equal to, by m is equal to mu, which is also called as mobility, right? So mobility is nothing but drift velocity acquired per unit electric field. Now go through these definitions, children. I'll be continuing with the definition of drift velocity and mobility in the next class. So before that, I want you to go through the introduction and be very thorough with whatever we have discussed. Okay, ma?